torque is really a force that creates or causes rotation. That's what a torque is. And the equation for torque, we use T or tau, whatever you want to call it. It's R times F. What does that mean? R times F. Now, if you have a rusted nut here on your bicycle and you're trying to loosen the wheel on the bike, and you bring in a wrench here, here's your wrench, I feel like Picasso now painting this picture, and you put the wrench and you push down here. You start pushing down with a force of 100 Newton. And let's say the wrench is actually here is, I don't know, 25 centimeter. The distance from here, center to the center. That distance is 25 centimeters. How much torque are you creating trying to loosen that nut? The torque is going to be R, which is the distance from here to there, that's 0.25, times the force, which is what? 100 Newton. When you multiply, that's 25. And the unit for torque, let's think about this. What is the unit for force? Newton. What's the unit for the radius? Meter, Newton meter. The torque is 25 Newton meter. Now, if you go and get a small wrench instead of that big one, again, the same nut here, and you get a small wrench, and you apply the same force here, but the radius here is 10 centimeters, 0.10 meter. How much torque are you creating here? 0.10 times what? 100, which is 10 Newton meter. Notice the torque you're creating is not a lot of torque. So again, if you try to change a flat tire in your car and you get a small wrench, you're trying to loosen that nut, good luck. That's why when you pull the jack out, the handle for that piece is about 2 feet. Because the longer the handle, the less you have to pull with it. The shorter the handle, the more you have to pull with it. Now what about if you pull on an angle now? Notice another thing about R and the force. What is the angle between the force and R? 90 degree. You're going to see us change that equation in a minute. So it's going to say torque equals R times F times sine theta. Because if you push horizontally, if I go and push horizontally on that, that will not create any rotation. You have to push vertically down to make it rotate, spin. So here theta for this example, both examples, theta was 90 degrees. What is sine of 90 degrees? 1. That's why I didn't use it. So what about if you're riding your bike now? Just look at this. And you're pedaling. Here's your bike. And the pedal is like this. And let's say that distance from here to there is 0.2 meters. And you push down. Of 980 Newton. That's a lot of force. Why did you come up with that number? 980 Newton. What is the force that you push with if you're riding your bicycle? Isn't it your weight? And usually if you ride your bike, you see these guys who are professional bike riders, you see their body shift side to side because what they're trying to do Try to put all the weight on that leg when they're pushing, then all the weight on this leg when they're pushing, because you want that force to be the bigger the force, the more torque you're going to have. That bike is going to spin faster. You see, I'm going left to right the whole time, their body, because they're trying to move that weight back and forth. So if you take somebody who's 100 kilogram, like about 220 pounds, their weight about 980 Newton. So if you can take the entire weight, put it on one side, on one leg there, that's a force of 980 Newton. Do you really get the entire weight on one leg? No, but I'm pushing it, exaggerating. I could make it maybe 600 Newton. That's more reasonable, because you can't get the entire weight over that side, even if you try to. What I need to know is what component, because this force, I need to figure out what that value of the force is. So I need to give you what the angle is. We need to know what that angle is. What is this angle? Let's say this angle is 30 degrees between the vertical and that. So I need to figure out what portion of that force is in this direction. And because I'm giving you the angle with respect to this, now a few minutes ago I wrote a sine theta. It's sine as long as the angle with respect to the x-axis. But now the angle with respect to the y-axis. Remember, if I want to get this component of the weight, this piece, this is the side that's adjacent. And the adjacent is always going to be what? Sine or cosine? Cosine. So in this case, that force here will be the 600 Newton cosine the 30 degrees, because that's the adjacent. Notice if you look at your triangle like this, that's the opposite. This is the adjacent. I'm looking for this value. And roughly that's 52 Newton. So what is the torque? The torque is going to be 52 Newton times the 0.2, which is what? 10.4 Newton meter.
Could you set that up in one equation to have it be torque equals 0.2 meters times 600 cosine 30?
I could, or if I use this angle, right? If I use this angle, then this value becomes what? The sine. So what our book does, they use the angle with respect to x. If you see with respect to x, they use the sine because that's the opposite. And so that's what, if you look at the book, it says torque equals force times r times sine of theta, as long as theta was given to you with respect to what?
The x-axis.
To the x-axis, yep. If theta is with respect to the y-axis, will be f times r times cosine theta, if theta with respect to y-axis. And again, it goes back to Sakatoa. Sine opposite over hypotenuse, cosine the adjacent over the hypotenuse. This triangle and that triangle are the same. If we use this angle, that's the adjacent. If we use that triangle, that's the opposite. So that's why. The other thing to remember, what about if you push straight down? What about if you push when the pedal is like this and you put your weight on to push straight down? You put your 600 Newton down here. Guess what will happen? What's the torque here?
Well, it would be 0.
Zero. If you push down, there's no way that bike is going to pedal, is going to move. If you have a bicycle and you just put the pedal straight up in the air, you stand on it, that bike is not going anywhere.
Has to have an angle.
Yep. Has to have an angle or horizontal, some way to move it. So the torque here is 0. And the reason is why 0, if the force goes through the pivot point, that's the pivot point. If the force goes through the pivot point, it has a 0 torque. So if you watch me, if I walk into that door and I push on that hinge straight on that door, if I push straight on, it's not going to spin. I can push as much as I want. It's not going to spin this way or that way. But now if I push on it this way, it's going to open and close. Right? Doesn't take much force to make it open and close. Why is the handle put at the end of the door, not at the beginning? I got to push much, much harder here to open the door versus right here. A lot easier to open it from here than from down here. So if the force, and if you look at it, the force actually, if we're using the sine, because the angle with respect to the x-axis, well, if this is like, if you look at it, what's the angle here between these two? 180 degrees. And what is sine of 180? That's 0. So the torque for that will be always a 0. The torque is a force that creates rotation. By pushing down on this, it's not going to make this one spin. Actually, when I get to a traffic light, when I ride my bike to school, I get a traffic light. When I stop, I stand on the bike, and my pedal will be right there, straight up in the air, or down, up and down. And I'm standing on it, and it's not going anywhere. I'm not pedaling. The thing is not spinning. Because I don't want it to spin. I'm waiting for the light to change. The minute I want it changes, I push that pedal just a little bit to the left or to the right, and I put my weight on it, and the bike will go forward. Now, can the torque be positive? Can it be negative? Yes. Torque can either be positive or negative. How do we know the torque is positive or the torque is negative? Let's see. The torque is positive, meaning greater than 0. If the torque causes a counterclockwise angular acceleration. If the torque counterclockwise angular acceleration. Another way of saying it, if they start to spin counterclockwise, and the torque is negative if we have what? Clockwise rotation. Make it easier on us to say it. An example, let's see whether the torque is positive or negative. You take your nephew to the park, or your niece. You go on the seesaw. This is my seesaw. It's 4 meters long, so each one is 2 meters. There's a pivot point here. So it's 4 meters long. So this end from this point is 2 meters. And you put your little nephew or niece here. And let's say the mass of your nephew or niece is 15 kilogram, about 35 pounds, 20 years old.
The whole thing is 2 meters, you said?
The whole thing's 4.
4, okay.
That's so this is 2 meters from here. If you go sit on that end, it's no fun. That seesaw is not going up and down. So normally you go and you sit somewhere here. That's you. And let's say you sit at 0.6 meters from the pivot point. Everything is measured from this point. And your mass is, I don't know, We'll say 70 kilogram, about 150 pounds. Can you tell me what the net torque is on the system? Now I'm going to calculate the net torque of the pivot point right here. The reason, once I pick that point, I can neglect the weight of the beam. Why? The weight of the beam will be what? Which way? Straight down. And the pivot point is pushing which way? Up, normal force. We said any force that goes through that pivot point, this point of rotation, has zero torque. If you think about it, the distance, this is perpendicular to the beam, but what is the distance from the weight to the pivot point? It's zero. It's going through that piece. So these two have no torque. They do not create any torque. They don't make the beam spin. When you walk into the park, if you look at it, that beam is horizontal. That means there's no net torque on it. If there's a net torque, it's going to go one way or another. It's going to be hitting the ground this way or that way. Once your nephew or niece sit on it, what will happen? You'll see that piece goes on this end up and this one goes down. So let's see what the net torque is. Let's look at your nephew or niece. It's going to make it move which way? Clockwise or counterclockwise, your nephew or niece? That's counterclockwise. That's a positive torque, right? Torque is what? Mass, or not the mass, the weight, force, times R. Well, the force is what? The weight of your nephew, which is 15 times 9.8. And how far your nephew or niece sitting from the pivot point? 2 meters. That's a positive torque. You say, what happened to sine theta? Well, theta here is what? 90 degrees. The weight of your nephew and the beam, they make 90 degrees. Your weight straight down, the beam is horizontal. Sine of 90 is 1. Now what about you? You sitting right here. You're going to make the beam spin which way? Clockwise or counterclockwise? Just your weight itself. If you sat on it by yourself. Counterclockwise, that's a negative torque. And the force is your weight, which is 70 times 9.8. The distance, which is what? 0.6. And sine of 90 degrees. That's what the net torque on that.
Z's in here.
I'm always here.
Yeah, he's always. Wait, you live here at 10:30 as well?
Yep.
Oh, okay.
70 times 9.8 times 0.6. So what's going to happen here? If you think about this, that's a negative torque. The net result, negative what? .1176, and that beam is going to spin upward, and you're stuck there. You know, this beam will be touching the ground and will look like this. After you both sit on it, where you sat there, the beam will look like this, touching the ground. That's what's going to happen to that beam. Well, that's no fun for either one of you. So if you want to go up and down, bounce, keep going up and down, you push up and you go up and down, then we need to slide you forward. Because you want to make sure that the torque on this end equals the torque on that end. So my next question, where should you sit? That's you. Where should we move you? How far from the pivot point such that the torque will be, the net torque equals to 0, so you can have fun going up and down. Because that's what the whole idea when you go on the seesaw. You go up, then you come down, you go up, come down, go up, come down. So you want that to be balanced. So where should you sit? So here's part B now. We're going to figure out where you're going to sit. So before you go to the park next week, do all the calculations. Ask your nephew and niece how much do you weigh. Do your math. So when you get to the park, you know where to sit. We know this is that 15 kilogram here. The 2 meters. This is U here. 70 kilogram. And the distance is X to the pivot point. So the torque will be, let's see, again, the weight here, which is 15 times 9.8, that's the weight, times the distance from here to there, which is 2. This will be a minus, because that will make it move clockwise. The weight of yours, which is 70 times 9.8, times the distance from here to there, which is X. $70 times 9.8, that's 686x. You want that to be 0. You want the net torque to be 0, so you can play there. $686x equals 294. X should be what? 294 divided by 686. 0.43 meters. So if you sit roughly about 0.4 meters, then you can have fun. You can go up and down. So that's the definition of torque.